Hi, everyone. Thanks for coming. So my name is Jason Deere. I'm a software engineer at Cloudera, and I'm part of the Hive team. And today I'm going to talk about what's new in Apache Hive 3 for HTTP 3.1. So for the agenda for the talk today, I'll talk about some of the features that went into Apache Hive 3. I'll also talk a little bit about Data Analytics Studio, or DAS for short, which is a visual tool for Hive, which is new for HTTP 3. And I'll also talk a little bit about what's coming soon for upcoming releases. So first, Apache Hive 3. First off, just quick introduction to Hive. It's kind of the original SQL engine on Hadoop. So the front end consists of Hive Server 2, which is a JDBC server, which is responsible for receiving connections, compiling queries, and then submitting the query to the cluster for execution. Kind of the execution of queries, it's evolved from running on MapReduce to running using the TES execution framework on Yarn. To executing using LLAP, which is basically persistent daemons on Yarn, which kind of provides data caching and container reuse. And your tables in Hive, they can be stored on HDFS or S3 or whatever other cloud file systems you have available. So. For Hive 3, a lot of the work that's been done has been, focusing on trying to support BI tools directly querying Hive. So, a user clicking a button and, waiting for an interactive response time, and, the query actually goes to Hive to answer. Basically, being able to run 250,000 queries in an hour with Hive and LLAP. Some of the stuff that we've added, like the query results cache. So basically, Hive can save the results of previously run queries, so that rather than having to actually run the query again, it'll just give you back the saved results. We've added query workload management for LLAP. That basically improves the concurrent query execution when running on LLAP. We've added active, passive, high availability for Hive Server 2. Let's see what else. Materialized views, constraints. Let's see, ACID v2. Basically, we've made a lot of improvements for ACID for performance and other stuff. Also, improved Hive support for for tables on cloud file systems, and we've also improved Hive's query federation ability. So basically, you can define data sources, on JDBC, Druid, or Kafka, and basically treat them as Hive tables. And Hive will be able to kind of federate the queries out to to those data sources when you have to. So I'll talk about some of these features in a little bit more detail. So materialized views is one thing. So basically, this materialized view allows you to pre-compute a query. So you'll define a view based on a query, and what the query optimizer is able to do is it's able to recognize that you already have a saved result in the database. And you can rewrite, subsequent queries coming in so that they can use these pre-computed results. So this is different from the query cache, right? It doesn't have to be the exact same query. Basically, the Hive optimizer is basically it understands the semantics of the materialized view, and so it's able to make transformations based on the view to satisfy the query. Oops. So kind of, as I mentioned, basically, it doesn't have to be a full match. We support partial rewrites and to be able to fulfill the query. Also, with updates to the table, if it's defined on transactional tables, Hive will be able to detect if your view has been invalidated because of writes to the table, and so by default, Hive won't reroute queries to a materialized view if it's detected to be stale. On the other hand, if you want to trade off accuracy for performance, you can basically add settings to be able to tolerate a certain amount of staleness in your materialized views. We also have support for incremental updates of the materialized views. So rather than having to completely update the view from scratch, Hive is able to kind of smartly update the results, just based on the new data that's changed. Obviously, some it depends on the aggregates that you're using in your view. Some tables might require a full refresh depending on what kind of aggregations are defined. So that's kind of a little detail on materialized views. I guess if you've used other database systems, you may have be familiar with them. So now we have them for Hive as well. Constraints and defaults, also something that you might be used to from other database systems. Now we have them for Hive. So constraints are useful for being able to produce better query plans. Primary and foreign key constraints, they're soft constraints. They're not enforced, but they're very important for being able to allowing the optimizer to remove unnecessary tables from your joins. Not null constraints, on the other hand, we actually do validate those and insert, similar for column values. So those are kind of useful features for users that expect those. We've also added database catalogs to Hive. So you can now use Hive to query the state of Hive, right? So you can look at what table, so you can say find what tables are there. For these example queries, like you could say, hey, what tables are in my system that have the column name with SSN in it, or if you want to find the largest table in your database, basically you can check the table stats in the catalog to see what the largest tables are. Oops. Okay. So connectors. So for Hive 3, we have improved query federation. So basically, you're able to define Hive tables based on external data sources that you've defined and use them in Hive. For example, kind of going back to the to the idea of the database catalogs that we've added to Hive, how did we actually create that? So we have a JDBC connector, which basically allows you to create a Hive table based on a query from a different relational database. For right now, I guess it supports kind of read-only queries. But yeah, so that you can, and so I guess kind of here's the example here where we've defined a particular table based off of a Postgres query. And the optimizer is kind of smart enough to do automatic push down of certain expressions. So like joins, aggregates, filters. If the optimizer detects that this can all be done within the remote database system, then it'll basically push that all down and send the the query to the database, to the remote database to run, rather than having to pull everything from the database and do it in Hive. We also have the Druid Connector, so that allows you to create Hive tables based on a Druid data source. So for the example that we have here, kind of a nice example actually. So we've created a Hive table backed by a Druid data source, and at least based on adding the Kafka settings that we did on this table, this Druid data source itself is populated using a Kafka topic. So kind of you have Hive, Druid, and Kafka all kind of working together to be able to create a Hive table. We also have, again, smart push down of expressions to Druid. So in our join example here, where we have a join between the Druid table and the table in Hive, and here Hive is able to generate a Bloom filter based on the customer's table, which lives in Hive, and basically push that Bloom filter down to Druid in order to in order to greatly reduce the amount of data that actually gets sent over to Hive in order to perform the join. And so if you're interested in learning more about how Hive and Druid work together, I definitely recommend checking out Nishant's talk, which is at 4 o'clock today. And you can also, so we have the Kafka connector, and so you can actually define Hive tables directly on a Kafka topic. So here we have an example of a couple of examples of creating Hive tables on top of Kafka streams. And so here in our insert example, effectively we're populating or we're publishing to the second stream using a Hive query, where the query is actually reading from the first stream, and then calculating the current 5-minute average of the stock prices, and then performing the insert to the table, which effectively is publishing to the second stream. I'll also talk about ACID for Hive 3. So we first added transactions in Hive in version 0.13. This provides safe reads on a table, even if another query is performing update operations at the same time. So for Hive 3, we've done a lot of work on ACID. So we've kind of reworked the way that ACID storage works, and so that's kind of had a lot of positive effects. So performance now is just as good as ACID tables. So for our latest round of performance benchmarking, we actually ran our TPC-DS queries on using ACID tables. So basically, the performance penalty is kind of gone with the ACID tables. Also, we no longer require bucketing columns for defining your ACID tables. We also support kind of insert-only ACID tables, and so that actually allows you to define ACID tables on non-ORC formats. So you can create ACID tables with text, Parquet, or other formats. And we've also improved support for ACID tables stored in S3 or other cloud storage systems. And so now, actually, with all these improvements, we've actually made ACID tables kind of the default table type for Hive 3 in HDP. So if you create tables, they're kind of created as ACID by default. So kind of just showing kind of the differences between what the syntax looked like for creating ACID tables. So for version 1, you had to add the bucketing columns. You had to add the properties to set that it's a transactional table. And now in HTTP3, it's just a pretty straightforward create table statement to create asset tables. So workload management. So this is something that we've added to LLAP. So in the previous versions, prior to workload management, running multiple queries on LLAP had the potential for race conditions and resource starvation for some unlucky queries if you're running multiple queries at the same time. So with LLAP workload management, basically you can add policies to provide better sharing of the LLAP resources in a multi-tenant environment. So basically, you can split your resources up into different pools, which kind of guarantee a certain amount of resources for your queries that are running. We also provide query guardrails, which can allow you to protect the system from queries that are taking too long or using too many resources. You can actually take actions to prevent those kinds of queries from kind of running and kind of taking over your system. And the scheduler in LLAP basically is it allows you to run. If there's no competition, if you're the only query running on the system, it'll allow you to take up up to the entire take up the whole cluster if there's no other competition for resources. But it's smart enough to know that once there is contention for resources, basically the fairness policies will start to kick in, and let's say if one query was taking up all the resources, basically you would start to see some of the work getting preempted in order to ensure fairness to the other queries. So kind of two parts that we've added to the workload management are resource pools and triggers, and I'll touch a little bit on this. Actually, I'll first go into the resource plans or resource pools. So what you do is you actually you basically define resource pools in order to divide up the LLAP resources. So in this example, we've created two resource pools, BI and ETL, and so for the BI pool, that is basically able to take up 80% of all of the LLAP resources. And what we do, and then it also has a query parallelism setting of 5, which basically means that we will kind of guarantee fair sharing of resources for up to 5 queries running at once on this pool. And then the ETL one basically gets 20%. Users get assigned to a pool by default. In our example here, let's say most users would default to the ETL pool, but then we can create mappings so that so other users, let's say if they're designated to be BI users, we can say, hey, we want them because they are because they're interactive users, they expect interactive response times. We want to give them more of the resources to process the query faster. So we can set those guys to use the BI pool. So it's kind of it's kind of a little analogous to kind of like to yarn queues, I guess. And so this is kind of how we kind of allow kind of more better kind of sharing of the queries when they're running in a concurrent environment. And so what we've also added is the guardrails, or basically the triggers for guardrails. And so what we do is you can create triggers, which are basically they're actions that you define to occur once a condition is met. And so, for example, some of the conditions might be, you basically if the query is taking too long, or if it's taking up too much execution time, or you are reading or writing too much HDFS bytes, then you can basically kind of set conditions where will take specific actions. If we reach those conditions. And so, for like in this example, basically, if you hit an execution time greater than 2,000 seconds, then you can say, hey, this is taking too long. Kill the query. You can do other actions besides just killing them too. Going back to the resource plan example, here we've defined a trigger where if the total runtime goes above 3,000 seconds, then we will move it from the BI pool over to the ETL pool. So then so basically at this point we've decided that that this query is no longer an interactive query. We'll just treat it with lower priority and give it less resources. So this is kind of what we have for workload management for LLAP. So performance. Performance has always been a big focus for Hive with HDP. So we do a lot of TP-CDS testing. At this point, we're now able to run all 99 TP-CDS queries on Hive, and we've made big improvements with every release against these benchmarks. So just showing one benchmark. This isn't even our benchmark. This was an independent one, which was done by Postech University. Basically, they ran a benchmark against Hive on LLAP, Spark, Presto, Hive on Tez, and also Hive with MR3. And kind of the results of that benchmark basically showed that Hive 3 on LLAP was kind of the fastest in aggregate, in terms of overrunning all of the queries. So, some results. So, some of the improvements that we've made in performance for HDP3. So we have improved vectorization. So we have, so basically we've been able to vectorize the execution for partition table functions, for rollups and grouping sets. And so, that helps a lot for kind of OLAP style queries where you end up doing a lot of aggregations over a lot of data. So as you can see, for some queries, this can show some really big gains. We also have the shared scan optimization, and this is a query optimizer improvement where if a table is kind of scanned multiple times in the same query, sometimes we can actually get away with only reading the table once. So this, for query 28, this ended up, being a 4x improvement for us for Hive 3. We also have the dynamic semijoin reduction. So this was, this is able to, have a big effect on kind of the amount of rows that you end up having to read to process for a join. And so effectively what happens is on one side of the join, you basically build a Bloom filter and then basically send that Bloom filter with the IDs for the rows that you'd be joining to the other side of the table. And you basically use that as a filter to kind of reduce the number of rows that end up being processed for your join. And so in some cases, if you have, fairly selective predicates, this can be a huge reduction in the amount of data that actually ends up having to go down to the join. And in the case of query 72, this resulted in a 7x improvement. So, basically a variety of both query optimization and kind of runtime changes that resulted in improvements for Hive 3. Okay, so that's kind of what I'll cover, what we covered for Apache Hive. I'll also talk a little bit about Data Analytics Studio, or DAS. So this is a visual tool that we added in HTTP 3 to help you optimize your Hive queries. So basically, this gives you one place to explore your database, to troubleshoot slow queries, and to look at usage patterns in your tables. So so one thing, first things that we have for DAS is it comes with a query pane with autocomplete of your tables and databases and columns. So it basically allows you to execute queries or get visual explains for your queries. It also comes with a data explorer that allows you to browse your data, browse your databases, and so you can take a look at your tables and kind of view the schema, the stats, and the sample data for your tables. It also keeps a history of all of the queries that have been run on Hive. And so we're not just talking about the queries that we just ran on the query pane. It actually is able to. It actually keeps saves all of the queries that have been submitted to Hive from whatever query tools you might be running. And so so basically if a customer was complaining that that their Tableau queries were running slowly, you can actually go to this to your queries history and find the query that was run, and you can kind of see and drill down onto that query and see what was taking so long. It also comes with kind of some helpful filters to basically help you look at some common categories of queries. For example, if you want to look at queries that took longer than 10 seconds, then you can quickly go to that and it'll give you the list of those. So drilling down to specific queries, so basically we keep a ton of information for each query. Basically, if you're familiar with the Hive view and the TES views from HTTP 2.6. Basically, it has everything from that and more, right? It has so it has a query text, kind of has the query details, the visual explain for the plan, the configuration settings for the query at the time that it ran, also the query execution details, so you can kind of look at the query DAG and the stages of the query and how long those took. So yeah, again, basically, all that's probably similar to what you would have seen from the TES view. But basically you can see it all in one place. Also, what we've added is basically recommendations for your query, and so that kind of shows up at the top of the page. So it might give you suggestions like this query actually ran on a table that didn't have stats run, and so you might want to consider running stats for this table. Or this is a text format table. This actually could be faster if you used ORC or something. So those can be that can be very useful for trying to speed up your queries. It also has a query compare facility. So basically, you can do kind of side-by-side comparisons of two different runs of the same query. So this is kind of an example. So basically, there were two runs of the exact same query. One of them took 3 times longer. So you can take a look at the time at the DAG execution, and you can see that it took a lot longer for query A compared to query B. And if you actually look at the differences between the configuration settings between the two queries, you can actually see that map joins were disabled, when I ran the query the first time, and that's why it was that much slower. I guess I didn't have space to fit on this slide, but if you showed the query plans from the comparison, they would also look different too. So this is kind of a very useful facility to help look at why did the query run differently one time compared to another run of it. DAS also has kind of heat maps and join reports to allow you to kind of show usage patterns, across all of your queries on your data. So kind of the heat maps can show you the most frequently accessed tables and columns, and the join reports kind of can show you the most frequently joined tables and columns. So it's kind of very useful for getting kind of global usage patterns on your tables. So DAS, it's basically available as part of HTTP 3. Basically, it replaces the Hive and Tez views that were in HTTP 2.6. Basically, we have kind of regular updates to DAS, and basically you can install it and upgrade it separately from the rest of your HTTP stack. So now we can talk about a little bit about what's coming up for HTTP, or actually not, or for Hive. So kind of the stuff that I talked about is available in HTTP. So all of this and more will be available for the upcoming CDP for Cloudera. So what kind of stuff are we looking at? So we're talking about Hive on Kubernetes. So basically, easy and fast creation of deployments for new Hive compute clusters. So basically, if you want a new Hive server and LLAP, you can basically deploy a new one with a few clicks of a button. Also, integration with SDX, which is the kind of the shared services layer for Cloudera. Basically, the Metastore and the security and governance layers. Allows you to have multiple versions of Hive. So let's say that you have an existing workload running on a Hive Server 2 instance that you have. Maybe you don't want to touch that one, so you can leave that one as it is. But you want to play with the latest and greatest from the new versions of Hive. Then you can basically start up a new compute cluster without having to touch the other one. And also, we'll support rolling patch upgrades with Hive and Kubernetes. And then for Data Analytics Studio, we're going to add kind of new recommendations, including recommendations for materialized views, kind of based on some of those kind of global usage patterns information. Also, new visualizations for query execution. In terms of Hive connectors, so we'll make sure that the Hive on Kubernetes is able to have proper integration with any managed streaming or relational services that you might also have in your cloud. We're also adding working on a query scheduler for Hive. So this will allow you to basically run queries at a regular schedule. So you can basically do like micro batch streaming queries with Kafka, or you could do automated materialized view updates or statistics updates for your tables on a regular basis. And also for what's new for ACID, we're working on being able to provide APIs to allow other applications to have better integration with ACID tables directly. And so that's kind of the talk. Thanks for coming. If you guys have any questions, please come up to the mics.
Thanks. So my question is a bit comparison with HBase. So I know that Hive was always meant for analytical use cases, OLAP style, and HBase more for this kind of OLTP supports also ACID. And now you bring in a lot of ACID to Hive, and I am confused actually. In which case should I then continue using HBase? In which case Hive? And why we need ACID in both of them?
So I definitely don't know a lot about HBase, but I think obviously if you're trying to do kind of more point lookup style stuff, that's that would be better for HBase, I would think. Yeah. So for Hive, we definitely need ACID for Hive. Right.
But for me, ACID means more OLTP working. What kind of OLTP actually is an Hive support?
Yeah. So the ACID support for Hive is definitely not OLTP. It's really meant for a kind of occasional updates to your data, as opposed to being able to constantly update the data. So yeah.
Thanks.
Mm-hmm.
Does the cloud storage integration with ACID support updates and deletes?
Yeah, I believe so. I mean, yeah, it would at least. Yeah. So if you're working with the full ACID tables as opposed to the insert only ones, yeah, they should support updates just like we do for the ACID tables on HDFS. Yeah.
Thanks.
All right.
Can you throw some light can you elaborate more on the caching bit? How is it caching, and what happens if the query is going to different Hive servers?
Okay. So you're talking about the results cache that I was. Okay. So yeah. So right now the caching is really at the Hive server 2 level. Exactly. So if there's multiple Hive server 2s, so if you hit the one that has a cache, you'll get it. If not, then yeah, then basically that instance would have to cache the query as well. But then once they're both cached, then they can both serve the results as cache data. There is some work that someone's looking at possibly trying to have it between Hive server 2s, but right now it's just within one Hive server 2 instance.
So just to follow up, so what kind of cache tuning you support right now, and is the cache on heap or off heap?
So it's so this is so it's not this isn't on really it's saved on the file system. So basically what happens is what we've done is so when Hive runs a query, we basically save the results to a temporary location on the file system, right, on HDFS. And so usually what we would do would we just delete it at the end of the query. And so now we actually just keep track of that thing and we don't delete it now. And so then we can basically reuse it if the same query comes in. So that's kind of how it works.
Thanks.
Yeah.
I had a question about the external tables.
Mm-hmm.
Like you said that right now you can create external tables on external sources.
Yeah.
So for example, if you have a Oracle machine from which right now we are importing the data from,
Okay.
can we just create an external table in Hive and we have to stop importing it?
I mean, you can, well, it'll allow you to basically read from that table as if it was a Hive table. I mean, I guess it probably depends on, I don't know how much, performance stuff testing we've done on it, but I mean, I guess it would probably depend on, whether or not it, how often you're running the query or what kind of performance issues you're seeing there. I don't know if it makes sense to import it or not. I guess it might depend on your use cases. But yeah, you definitely can basically access it directly from, from your.
That's really
from your
fantastic. I just wanted to check it,
Okay.
double check. Thanks.
Is there an integration with Apache Kudu planned or on the roadmap?
I don't know if we have that on the roadmap yet. I know there's been some talk about it, but I don't myself know about anything concrete yet.
Okay.
Yeah, thanks.
How is Hive LLAP combining with other types of workload? So like I can run multiple things like Spark, HBase, other things in the same cluster, or I need to separate them?
Okay, so LLAP basically, so they're kind of persistent daemons that sit on the cluster. So basically what will happen is, when you start up your LLAP cluster, it still lives in the Yarn cluster, but basically it grabs a chunk of the cluster and it stays there. And so any other applications that you're running basically are they get the remaining space that you have in your cluster.
So it's actually recommended to separate the workspaces, workloads in different clusters. For cloud, it's very easy.
I think it depends. I mean, I think it depends, right? I guess you can have a heterogeneous environment. It's just that LLAP itself requires a certain amount of the cluster. So, I mean, you basically would just have. Yeah, I mean, I guess you can split it out, but I mean, or if you're trying to run them all in the same one, basically you would have to know that LLAP is taking up a certain amount of your cluster capacity.
Okay.
Yeah.
Does Bloom filter works if I use subquery as a predicate? I mean, dynamic filtering?
For the, sorry, say it again.
Does Bloom filter works if I use a subquery as a predicate in the where clause?
I believe so. I mean, I guess we definitely have got it to work in for certain classes of queries. I mean, there definitely were some where we weren't able to do it, but yeah, I believe that it should work for some subqueries.
Okay.
Yeah. All right. I think we might have to go to allow time for the next guys, but I'll be outside if anyone wants to ask more questions. Thanks.